amount of words you need. And so none of these are just like excess information. Each one I have condensed a whole entire concept into just one statement. So each one of these is important to understand. Okay, so when we're writing formulas as an acid or a base, and then we write it losing a hydrogen or gaining a hydrogen, what we have done is created something that is referred to as a conjugate acid-base pair. And so when we just put a hydrogen onto carbonate, that was like, it's a base. And then we added a hydrogen on the other side. And so the formulas only differed by one hydrogen ion. They both had CO3. One of them had an H, and their charge was off by 1. -2 versus -1. That is a conjugate acid-base pair. It is a formula that you get by removing a hydrogen or putting a hydrogen on, but specifically an H positive. If you remove an H negative, it's not conjugate acid-base pair. That's something else. Okay. So I've put here the two options. If you're looking at a base, then the formula that's a base will accept an H positive. So you just add a H positive to it, and that new formula is its conjugate acid. So when it acts like a base, bases accept hydrogens, you put a hydrogen onto that formula, and what you've created is the conjugate acid. That would be the base. That is its conjugate acid. What is the only difference in the formulas? One H positive. They both have NH3. One of them has one extra H. The one that has an extra H positive is the acid of the pair. The acid will always have one extra hydrogen. Just by definition, an acid has a hydrogen that it would lose. So if this lost a hydrogen, it would form ammonia. Okay. Okay. When it's an acid will donate an H positive, and the new formula that you write is its conjugate base. So if we have nitric acid and we remove a hydrogen, you get nitrate. So nitric acid and nitrate are a conjugate acid-base pair. So when we write this in terms of a dissociation in water, if we're looking at something that is weak, so if we dissolve something that's a weak acid or weak base, then we have an equilibrium. So there's going to be equilibrium constants. And since we have an acid-base pair, the weak base will have a Kb, and the weak acid will have a Ka. And they exist in water in equilibrium due to how good the acid is at losing a hydrogen and how good the base is at gaining a hydrogen. So if you condense it all down, this is the formula you get. You don't have to condense it because there it is. You would only ever need to use this if you needed a constant that you could not find in the chart or wasn't given to you. Okay. And so Ka would be the weak acid constant, and then Kb would be its conjugate basis constant, and they would equal Kw. So does anybody remember what Kw stands for? That is the equilibrium constant for water. So that was on the first or second page of our notes this week. That is 1 times 10 to the negative 14 when it's 25 degrees Celsius. So we're just going to keep everything at like a 25 degrees Celsius situation to make it easier. And once again, we are talking about the behavior of something dissolved in water. So that's why water's constant is used. This is the behavior in water. Water has been completely factored in. It is the basis of everything we're doing. Okay. To find the equilibrium constant of the acid or base of the conjugate pair, we have to look in OpenStax. So what I have down here for practice, Number one, we're going to provide the missing acid or base. So what I have done is I have put a formula in either the acid column or the base column. And what you do is if I put it in the acid column, what do I want you to treat it as? An acid. And if I put it in the base column, I want you to treat it as a base. So what you would do is you would either think back to what we've already gone over, which is an acid is something that donates a hydrogen. You don't have to worry about hydronium because this is just what happens to this formula. Or I summed it up right here. If it's an acid, it donates a hydrogen and forms its conjugate base. Whichever way, both of them say the same thing. I just used the word conjugate base and conjugate acid in this section. Okay, so what would be the conjugate base of H3PO4? H2, what? PO4, -1. They cannot have the same charge because one of them has an H positive and the other one does not. And so they're going to be off by either way you want to think about it. The base will be more negative or the acid will be more positive, both saying the same thing. Okay. So see if you can go through with each one of these and like look at the directions and think. You got to think to yourself, add a hydrogen, remove a hydrogen, which you got to think through that and see if you can provide the formula of the conjugate according to which column I put it in. Okay. I have it written here. I wrote it again down here. I don't know if I write enough times. The more you write things, the more it starts to stick with you. And so I do not recommend that you skip over writing things down, like little notes to yourself or what you've done. And we're going to do a calculation in a minute. And I recommend that you write down the calculation instead of just typing it in your calculator. Because then you'll just be like, I don't know where that number came from. And so by writing it down, you'll hopefully it'll stick with you longer. So when you have the conjugate acid-base pair, and this is going to end up being part of a dissociation reaction. One's on one side, one's on the other. But when you have the substance that's dissolved, that's either acidic or basic, you will always rewrite the formula having lost a hydrogen or gained a hydrogen. So you'll always write its conjugate. So they'll be on opposite sides. And so here they are. And it's important to label the substance that dissolves as either a weak acid or a weak base. And then its conjugate as its conjugate acid or conjugate base. So what I have done here is I've just put it in acid-base columns. So they're already labeled. And so the acid column is for its acid behavior. The base, the conjugate base would have a KB for its base behavior. And so the only place to find KAs is in Appendix H. And if you want to find a specific, like look up the number, it would be in Appendix I. That's what number 2 says. If it is weak, look in the appendices for the acids Ka or the bases Kb. So Appendix H is where you find Kas. Appendix I is where you find Kbs. So for every one of these that is weak, you should be able to find either the acids Ka or the bases Kb. And as a reminder, are any ions in the base chart? Is hardly anything in our base appendix? No. So anything that has a charge on it, you're not going to have to even look at Appendix I because it's not going to be there. There's only 5 molecules in our Appendix I. Okay. And so see if you can find the correct constant. And if there's not a constant, again, you only have constants if it's weak. If it's strong, it will not have a constant. So I'm just going to show you the first, and I chose phosphoric acid first for a specific reason, because I want to illustrate more than just what we're talking about. And so if we look at our first conjugate acid-base pair, our weak acid is H3PO4. The conjugate base is H2PO4 -1. So we need to find the Ka of the acid of that conjugate pair. But what you will find, if a molecule has more than one acidic hydrogen, it's called polyprotic. Protic for hydrogens, because hydrogen is a positive, and positive hydrogen doesn't have electrons, and so it's called a proton. We call it hydrogen, but oftentimes it's referred to as a proton. So polyprotic means it has more than one acidic hydrogen. So things like sulfuric acid, phosphoric acid, citric acid, those have more than one hydrogen. Carbonic acid has more than one hydrogen that would be considered acidic. And so what you'll find when you look up phosphoric acid is you will see 3 versions of it. You will see H3PO4, H2PO4 negative, and HPO4 -2. So in our example, we only have one conjugate acid-base pair. What is the acid of our pair? H3PO4. And so the Ka, which is the constant that we see, is 7.5 times 10 to the -3. Should we also copy down the constant for H2PO4, -1? What kind of table is this? It's an acid. And all these constants are K, A's. Is an A the same letter as a B? Is the A that represents, like what does the A represent? Acid, and B represents base, which are opposites of each other. Okay, so because they are opposites of each other, it's opposite behavior. And so H2PO4 negative acting like an acid is not the same thing as H2PO4 negative acting like a base. What does an acid do? Lose a hydrogen. What does a base do? Gains a hydrogen. So if we wrote down the number from that appendix H here, that would be its equilibrium constant when it acts like an acid. We want the constant when it acts like a base, which two different things. And so the only value that we can look up is the Ka. So when you have a conjugate acid-base pair, you can only find one of the values, and then you calculate the other. Okay, so you would look up and you would find either the Ka or the Kb, and then you're going to calculate the conjugate's constant. You cannot look both of them up. You can look one of them up or be given one of them, and then you use that to calculate the other. And so this is the one that's in the appendix. This is in appendix H. Okay. And so this one we have to calculate. Okay. So our formulas that we use are really short and simple, but then we have a few of them. This is not an equilibrium expression. This is just a calculation for the equilibrium constant. So we're using an appendix to look up a constant, but we need the conjugate's constant. And so we have to use this formula here, the Ka times the Kb of a conjugate acid-base pair is equal to the equilibrium constant for water, which is 1 times 10 to the negative 14. So you're going to have to use scientific notation correctly. You're going to have to rearrange this, which rearranging it will be water's constant divided by the constant you looked up. And so our Kb is going to be equal to 1 times 10 to the negative 14 divided by 7.5 times 10 to the negative 3. Every calculation is going to look just like this, which is going to be the constant that you have to calculate is going to be equal to water's constant divided by the conjugate's constant that you found in the appendix. Your number is going to be very small. And I just round it to 2 digits. Most of the constants we look up are 2 digits. One 1.3 times 10 to the negative 12. Okay. So what this is showing us, the numbers, it is a kind of a measure of how good it is at being an acid or a base. So if you have a larger constant, it means it's pretty good at being that kind of behavior. And so when it comes to these two conjugates, on one side of the equilibrium is the acid, on the other side is the base, so it's going back. The 7.5 times 10 negative 3, that constant, that is a pretty large constant. It is large enough that when we do a calculation, you cannot ignore the minus x. So the change is going to be big enough that you actually are going to have to use the quadratic equation. The ability of H2PO4 negative 1 to add a hydrogen back, to go back and be H3PO4, that's to the negative 12. That is an extremely small number. H2PO4 negative 1 is not good at adding a hydrogen back at being a base. So between these two conjugates, this conjugate is much stronger at being an acid than its conjugate base is at being a base. So if we look at equilibrium, you're going to, in this equilibrium, there's going to be a lot more H2PO4 -1 created than going back the other way. Okay, so for this one, we have HCO3 -1 in equilibrium with carbonate. So again, ions are not in the base chart. So you would have to look up the Ka for HCO3 -1. And but again, if you don't know the name of it, this is bicarbonate, but ion names are not in the chart. The original acid is. And so you would just try to find this formula right here. And so if you scroll through, you would find that ion underneath H2CO3. And so the Ka for HCO3 -1 is 4.7 times 10 to the -11. So that is in Appendix H. If it is an ion, you will have to write its conjugate acid and then look up its conjugate acid's Ka and use that to calculate the Kb. Carbonate is an extremely common base. So we're going to calculate it now, and it's now going to be in your notes. If you just remember that it's in your notes, you won't have to calculate it again. So you'll have already calculated it because it's part of a practice problem later. And also down here, bicarbonate ends up on the base side, so you can calculate its Kb. Okay, so how do we calculate carbonate's Kb? Since these are conjugates, then the conjugate acid base Ka times Kb will equal Kw. And so the Kb is 1 times 10 to the -14 over the number that we looked up, 4.7 times 10 to the -11. So that is 2.1 times 10 to the -4. So that's, when it comes to constants, if it has a constant of -4, -3, -2, even -5, it's not extremely weak, but it's still a weak base or acid. But fortunately, if we do a calculation for this, and when it comes to doing the math, we could actually simplify it and not have to use the quadratic equation. So in terms of equilibrium, the ability of carbonate to form bicarbonate and then bicarbonate to go back to being carbonate, HCO3 -1 acting acidic is not, that doesn't happen very often. Look at, that's a tiny, tiny constant. So in equilibrium between these two, this conjugate base is much stronger than its conjugate acid, just by looking at these two numbers. Okay, so for each example, you should be able to find, if it's weak, the Ka or the Kb. So if it's not in the Ka table, then it would be in the Kb table, or it's strong. Are any of the things on this strong? HBr. So what should we put right here? We can just put strong acid. And so we're not going to, there is no equilibrium with its conjugate. So when HBr dissolves in water, it goes one way to form its conjugate base. So that means that bromide, which is its conjugate, Bromide is not going to take the hydrogen back and create HBr. So if it is one way, it means this ion is neutral, which we've already figured out. So it does not have a KB because it does not have the ability of having the water surrounding it for that water to donate a hydrogen to it. Because if it donated a hydrogen, it would form a strong acid. Strong acids cannot exist in water as strong acids. They turn into hydronium. The reason that these ions are neutral pH is because every single one of them is the conjugate base of a strong acid. So if you dissolve chlorides or bromides or iodides, they're not going to be able to pull a hydrogen off of water because they would form a strong acid. That's why they have no effect on pH.